This is the problem that was put on your fifth quiz this morning and afternoon. We have a rectangle. Base length is 3 angstroms. Height is 2 angstroms. Remember, an angstrom is 10 to the negative 10th of a meter. At opposite vertices, at the ends of the diagonal, you have a proton charged E and an electron charged negative E. We wish to know what is the total force on a magnesium ion, doubly plused magnesium ion, placed at the center of the rectangle. In other words, placed at the midpoint of the diagonal line. We'll first calculate what the square of this distance A is. Same in both places, A and A. Well, the diagonal length is 2 times A. That diagonal is the hypotenuse of this right triangle. So the square of the hypotenuse equals the sum of the squares of the side lengths. So it's double A gets squared to 4A squared equals 3 squared plus 2 squared. A squared then works out to be 13/4. Now the units are angstroms, so it's square angstroms, which I rewrite in terms of square meters. 13/4 times 10 to the negative 20 square meters. Let's look now at the two forces that act on the magnesium ion. There is a triangle once again. That side length, that length is A, and so is that. We have that the net force on that magnesium ion is twice whatever that red force is, that vector A. I'll call that force A. That force arises from the pull by this negative charge on the positive charge. Now, whatever that pull is, it's the same value as the push on that magnesium ion, a push that I don't show in this diagram. A push from the positive to the positive acts in the same direction as the red arrow. So the total force is twice whatever the one force is, which I've agreed to call A. Well, let's repeat it down here to give more room. It's 2 times the force A, which is K, times E. Magnitude of this charge E is negative E, is E, times the other charge, which is double E. And then you have downstairs A squared. Let's put the numbers in. It's 2 times 9 times 10 to the 9th times another 2, and then E times E, E squared. All divided by 13/4 times 10 to the negative 20. This works out to be 2.84 times 10 to the negative 8 meter. I meant to say Newton, which I'll rewrite as 28.4 times 10 to the negative 9 newtons. But 10 to the negative 9 of a newton is a nanonewton. Final result, the force on the magnesium ion is 28.4 nanonewtons.